Good evening and welcome to the Vancouver Aquarium. My name is Jonathan Holtquist and I'm the host of the Vancouver Aquarium's Film and Lecture Series. Tonight's program, Radioactivity in Our Ocean, Fukushima and its Impact on the Pacific. You know, there are lots of perspectives out there and opinions about radiation, and they vary quite a bit. From nothing to worry about to the ocean is basically dead. The Vancouver Aquarium Marine Science Center is a scientific organization, and science is in our DNA. Scientific research was one of our founding pillars. We've invited speakers tonight that will share scientific facts with us, facts based on years of scientific observation of our natural world. After their presentations, you will have the opportunity to ask them questions about the facts that they present. We'll be taking questions online as well as here at the aquarium. Dr. Ken Bissler, our first speaker, is from Woods Hole Oceanographic Institute. He studies natural and man-made radionuclides in the ocean. Dr. Jay Cullen, our second speaker, is from the University of Victoria and studies trace elements in the ocean. I'd like to go ahead and invite Dr. Ken Bissler.
Thank you, Jonathan, and everybody for coming out tonight and tuning in online. So I'm from Woods Hole. We're outside of Boston. We have a very large oceanographic academic institution, non-for-profit, and we do all kinds of work. I've happened to be working in ocean radioactivity for about 30 years, kind of getting a PhD during the Chernobyl era when there were new releases, had studied the fallout. So I'm going to try and take you on a journey here from kind of what it looked like in Japan before Fukushima, that slide from Hokusai, to what happened on March 11, 2011, 4.5 years ago now at Fukushima Dai-Ichi, the reactors that overheated after power was lost due to the horrific tsunami that hit Japan at that time. We're going to look a little bit at how that radioactivity moves across the Pacific. So the ocean currents will carry this from the coast of Japan here over to our side of the Pacific. I'll get a little bit into how citizens have participated in helping us analyze what's there and some exciting new endeavors in trying to get wearable devices, trying to get people more engaged in monitoring this radioactive ocean. So I'm just going to start with some real basic lessons because I don't think people fully appreciate what's already in the ocean and what the sources are. And we're going to focus a lot on cesium, the isotopes of cesium, and they've been around ever since we started basically conducting nuclear tests on land in the atmosphere, mostly in the 50s and 60s. And we're going to add up how much cesium was released from these different sources. So global nuclear testing is about 1,000 in a unit of a petabecquerel. Now, we use these really strange units for something that you can't taste or smell or feel, so it's kind of hard, but I'll try and stick to becquerels, which are really a decay event per second. It's a very small unit, so you often have to put things like a peta, 10 to the 15th, in front of them to add up all of the cesium on land and in the ocean. We tried to show here by the amount under the water how much is in the ocean. Since it's an ocean planet, about 60% of that fallout is in the ocean. Oh boy, it is sensitive. And there's about 1,000 of these units, petabecquerels of cesium-137. Chernobyl was about 10 times smaller, about 85 to 100, mostly on land that was hundreds of kilometers from any ocean basin, basically a land-based disaster in 1986 in the former Soviet Union. And then we have over in Fukushima a range of numbers because we really don't know that well. Unfortunately, at the time of Fukushima, certainly we have better capabilities, but that's an ocean event. Most of the radioactivity went into the ocean, was poorly sampled in many ways, and so we have some estimates of what was delivered, and I'll talk about it in the next slide, as atmospheric fallout or direct water discharges, something on the order of 10 or 15 up to 60. I say it's comparable to Chernobyl, but for the ocean, this was unprecedented. This was right on the ocean, so much more the radioactive isotopes of cesium got in the ocean from Fukushima than Chernobyl. And as a reminder, 3 Mile Island is just a trivial number in these types of scales. You should also know that there's many naturally occurring radionuclides in the ocean, potassium-40 being the largest ones. So in these same units, 15 million petabecquerels of potassium-40 are in our oceans. That also decays. That's why it's measured in becquerels. Uranium-238 is another abundant one. This comes from weathering of rocks. Basically, in New England, we have a lot of mineral rocks. We have radon in our basements, so we have natural sources. And the challenge for me as an oceanographer is often trying to get at smaller amounts of cesium in and amongst these other naturally occurring compounds that also have radioactive decay properties. But be aware, there's both natural sources well before testing and these new ones that were introduced. I put this slide in. It's actually in the brochure that's out there, so you can actually spend more time looking at it, just to get right to the start of, what does it mean for me? And I think people need to appreciate this fact about, if you look at health effects of radioactivity, that's probably why most of you are here. You think it concerns you, it concerns me. And we talk then in units of doses. Microsieverts is the unit here you see these numbers, 001, 5, 40. This is the amount of a dose you'd receive from these various activities. And I'll point out already, I've been quoted several times as saying swimming in the Pacific Ocean is about 1,000 times less of a dose at the current levels of cesium and what we're predicting than even a dental x-ray. That's 5 in those units. Or my flight here from Boston as I came across the country, or the natural radionuclides that are in the foods that we eat. And so that's not to say it's zero, but when we worry about health risks, you have to get up to units about 100,000 times higher, sorry about that, to see an amount that would have a measurable health effect in terms of inducing cancers. So we often talk about radioactivity like it's all the same, but these levels matter a lot. And I'll show you off Japan how the levels in the water changed during the releases shortly after Fukushima Dai-Ichi. So you have that to go back to and make some comparisons later. So just going back a bit over what happened off Japan, 2011, tsunami came about 45 minutes after the earthquake shaking itself offshore, knocked out the power. A couple days later, these reactors, they automatically shut down. The control rods are dropped so that there's no new fission going on, but there's a lot of heat left behind because of these radioactive fission products inside the core of the reactor. So you have to keep them cool, or you get things like, in this case, the release of hydrogen gas, explosions that cause what we call the atmospheric deposition. I'm sure you remember the scenes on the TV of the explosions at the reactor. And that's when everyone was very concerned. Could they control that? Could they maintain those temperatures so it didn't get much worse? And thankfully they did. But most of the fallout then went towards the ocean. That's also good news for Japan. The winds tend to blow away from the major city of Tokyo. That's not too far to the southwest. And about 80% in the ocean, about 20% fell on land. And that would have been a few days after March 11, 2011, mid-March. The way they tried to and continue to keep these reactors cool is to put water on them. At that time, they were dropping water with helicopters. They brought in firefighting equipment. But through the heroic efforts of the Japanese who were working there, they were able to keep this under control. And that resulted, though, in direct discharge, water coming back into the ocean from Fukushima Dai-Ichi. The peak of that, I'll show you, is actually a few days to weeks later, early April, when that actually entered the ocean. Now, fallout on land can make its way back into the ocean through rivers, so runoff is a source that we continue to study. That's a small amount. It continues to this day, as does the groundwater discharge, both from the reactor and up and down the coastline as the fourth source. So those are all the 4 important sources from Fukushima Dai-Ichi that occurred. And in fact, these 2 rivers and groundwater flow continue to this day. So for this one plot, we'll spend a little time on it. Every red dot, just to kind of put you in focus, is a sample of ocean water off Japan, along the coastline, about as close as you can get to that reactor. They basically went out, the TEPCO workers took samples, studying a couple weeks after March 11 is when they got their first sample, and they put these out in press releases. And what they were recording is the amount of cesium-137, this isotope with a 30-year half-life. It sticks around for a fairly long time. In this becquerel unit, the K events per cubic meter of water, a big amount of water, 260 gallons. And what they were seeing were numbers when they first made the measurements over 10,000. Now, the highest number I had ever measured after Chernobyl was about 600. People had seen 1,000 in the Baltics. So this was alarmingly high. The level before the accident was about 1 or 2 in those same units. That's the level we see generally in the Pacific Ocean. So this is what raised concern, because as it went up and increased up here in early April, we got to 50 million becquerels per cubic meter. Now, yes, that is a level of concern. That's what's going to cause reproductive effects just by being a marine biota, say swimming in there as a fish, mortality. The good news for the Japanese, in many ways, the oceans, that they were able to stop some of the leaks, so stop the water from flowing by plugging basically holes. I remember certainly seeing images that looked like a fire hose of water going into the ocean, and the levels of cesium in that single stream was even about 1,000 times higher here than the peak here at April 6th. So alarmingly high levels, but it went down. They plugged some holes, but it didn't go back down to the baseline. So as you put something soluble in the ocean, the activity will go down if you stop the source. So right from the start, the Japanese scientists and we were saying that this really is still continues to leak, and to this day, I'll be going in a couple weeks back to Japan. We expect to see numbers around 1,000 becquerels right at the reactor itself on the coast of Japan. Put this in a little more perspective, though, of why there's a lot of confusion when people in Japan were saying it's under control or it's not leaking. Often they're talking about regulatory levels. So reactors are allowed to release a certain amount of cesium into the ocean. That tends to be a level that where you're not going to have these direct effects. You might still be concerned, and they are today, about fisheries. So consuming something as far as seafood swimming in there might be an issue, and they actually shut down fisheries in Japan. Jay's going to talk more about the fish. But the water levels at that time were tens of thousands of becquerels per cubic meter. The drinking water limit in the States is about 7,400. I think it's similar, or maybe it's 10,000 in Canada. That's the amount you can continuously drink every day before it's considered of significant health risk, something you could measure statistically in a large population. So these are low by that standard, but quite high compared to what we had ever seen before. So what happens? So I'm going to do the ocean here and show you a beautiful image of ocean currents, focusing on the Kuroshio. Here's Japan, and here these white lines show you the speed and direction of the ocean currents that we actually be moving. We're actually going to hear about debris. They move debris as well. But these radioactive materials coming here off Japan are going to move quickly out into the Pacific Ocean. How fast depends upon the strength of those currents, the time of year. We can make predictions early on. There were some models. Here's one of them. I think this is one of the better models by a scientist named Rossi. And so we're going to follow this plume here as it goes. Ooh, that didn't work. See if I can get up into my model. So a half a year, that was 2011 to 12, went pretty fast. We can do it again. That contamination has moved about halfway across the Pacific. What you'll also see, though, is that the colors start out red and they're turning blue and orange, so you're getting dilution along the way. Anything that's soluble like cesium, like salt in the ocean, can only decrease in concentration the further you get from the source. It's not even. There's streaks and other things in here that you can't see, small-scale features like you saw on that last slide, but generally they're decreasing as you move across. Let's go a little further here. 2013 is when we started to get phone calls. I actually hadn't thought a lot about the west coast of North America because you can see from those light blue colors, these models were predicting relatively modest amounts compared to, say, 7,000, a drinking water standard or other health standards. But people still were, I think, rightfully concerned about what those levels would be. Here's 2015, 16, we expected to be up and down the coast. I'm the guy who goes out on a ship and measures these radionuclides. I like to say all models are wrong, some are useful. This was a very useful model because it told us what to expect, but it didn't have any data behind it. And so what we tried to do, and when you brought this, say, forward to a government agency, they say, well, the numbers are so low, why should we even bother? Well, people are concerned, and I'm concerned. What are those levels going to be? So we started this crowdfunding campaign called Our Radioactive Ocean. .org is the URL at the bottom, basically to enlist citizen scientists to help propose locations. In my case, I'm at a not-for-profit institution. We asked them to fundraise for each site. It would be about $600 here for Vancouver. The type of equipment we use is quite expensive to analyze. As I'll show you pictures, sampling is quite easy. So we post results, and we have now something like over 60 locations, over 100 samples posted, donations from 500 odd people in the year and a half it's been up. And almost as important, there's a lot of information about radioactivity. What were the levels before Fukushima? How does that affect marine life and other things? So it's a lot about getting the word out, teaching people about ocean radioactivity. Kind of fun for me. I'm a research scientist. I don't generally hand over containers to kids to take samples where they want to go with their family on a beautiful day, but that's exactly what happened. This is Point Reyes, California, one of our first groups that got involved. They continue to sample every quarter because we expect those to change. I'll go through the pictures first, and I'll show you, talk about the map later. Here's Englishman's Bay, Vancouver. Lush Cosmetics, I'll give a shout out to. They're one of our biggest supporters so far, based here from North America in Vancouver. They were getting questions about the quality of water that goes into their products and seaweeds and other things, wanted to help support us. A group of surfers took it on themselves to go with a local radio station and go collect samples and use as a fundraiser. Classrooms, this is a junior high school in Santa Barbara. So we've gotten all kinds of people involved in different ways that I really can't control. It's kind of fun. It's kind of scary at first, but great to see these groups take control, make it an event, and try and do something that they think is important. Now, getting to the data. So I've got a lot of dots here. So the dots are the locations. A white dot means we could not detect cesium-134. If you've been keeping track, I talked about 137, sticks around 30 years before it decays by half. 134 is only here for 2 years before half of it's gone by radioactive decay. And so if you don't see the 134, you can't say that there's any signal from Japan. And at this level, 0.2, that's a research level measurement. The health and safety lab might measure down to 100 or even 1,000 becquerels because they're not concerned at these levels. But we can measure down to less than one of these units. The yellow dots is where we started to see cesium-134 show up. So those are positive. They're very low on any of these scales. Just a couple of weeks ago, we found one off San Diego. I'm actually not sure, since we don't have a lot of data offshore, how the currents would have carried it here, but generally you can see the currents move water in these directions. We were in the news, was it last fall, I guess, Ucluelet, British Columbia. We've had a couple of positive results here. This is dated September 14th. I'm just getting more numbers this morning because we had a ship come into Seattle. These are actually off the straits, but we found a couple numbers under 2 for the isotopes of 134 cesium, and we've seen it offshore. So it's starting to show up the way those models are predicting at levels that actually are similar to what they thought in the 1 or 2 extra becquerels per cubic meter. The 137 isotopes might be 3 or 4, so combined something like less than 10 is where we're at. Now, one thing I also want to do is point out that we're not the only group doing this through this citizen scientist program. John Smith has a program out of Dalhousie. They head out into the Pacific on a regular basis. This is a combination of his data and my data, so you see kind of this offshore feature much better when you get higher resolution than those yellow and white dots in the last plot. And we're seeing numbers up here of 3 or 4. 3.5, I think, is the highest in that range of 137. That additional cesium has come from Japan, and it's sitting here offshore. And you might say, you know, why didn't it move according to those currents? Well, I'm not a physical oceanographer, but they're very interested these days about the blob. It's a warm anomaly. It's warmer waters than average that's been sitting here for months several months offshore as a temperature, so this is not radioactivity, it's temperature of the ocean, an anomaly, how much higher it is than normal, a couple degrees here. And for the same reason that you're not mixing that warm and cold water, we're not mixing the cesium. So it's consistent both between labs for cesium and with what the physical oceanographers are telling us about mixing in the ocean and the exchange between the coast and the interior. And then a third group that's watching out for cesium, Kelp Watch. They formed almost the same time that we formed our radioactive ocean. They have 48 sites, something like 52 scientists involved. They've yet to see any 134 cesium in the kelp samples. So 3 groups are giving more or less consistent results along the West Coast. I think I'm going to move towards the final comments. One is, why do we care so much about cesium? There's other isotopes you've probably heard of. Well, this plot attempts to show you a whole range of this alphabet soup of radionuclides by the amount of radioactivity, petabecquerels. Again, becquerels times a large number, logarithmic because there was a wide range. But the light blue bars, they might be gray in the back, are the levels in 2011. The blue is what remains in 2015 due to what's called their half-life, this radioactive decay process. The health effects are often the most significant for things that have short half-lives, iodine-131, 8-day half-life, half of it's gone in 8 days, and that's the one that causes the concern for thyroid and thyroid cancer, particularly in children in Japan. But it's gone. So most all of these are gone except for the cesium isotopes we've talked about. Krypton-85 is a gas. It's also released in nuclear fuel reprocessing, mixes as a gas, so it's diluted quite quickly. I always get asked about plutonium. Aren't we concerned? It's a very, very small issue in Fukushima because it's about 1 million times less than the amount of cesium that was released, much, much smaller than, say, the residual plutonium from the nuclear weapons testing in the samples that we've analyzed, the biota, the waters, and the seafloor sediments. It's just not a big signal there, but it has a very long half-life, and it is a very big health concern. So we do pay attention to things even when they're there in smaller amounts. So other people are doing that. We just don't have time to show you the data. So a couple take-home points. I think it's important to realize that Fukushima, the nuclear power plant, is an unprecedented release of radionuclides to the ocean. We certainly expect to see the highest impacts close to Fukushima. So that means early on, and particularly on land, when it doesn't get mixed by those ocean currents. It stays underneath your feet. 100,000, well, talk about it. People can't move back to their homes because what remains in the soil in Japan. The fallout and ocean currents will cross the Pacific, but the levels are quite low. They're not zero, but they're similar, in fact, smaller than what we experienced in the fallout years. What do I lose sleep over? This is kind of the slide. It's that we continue to see radioactive leaks from that reactor. For cesium, I'm not as concerned. It would take actually, you hear like 300 tons a day, like you hear water volume. That really doesn't capture the contamination level, how radioactive is that water. So it would actually take about 5,000 years at the current levels of leakage to equal how bad it was in 2011 in the first month for cesium isotopes. So yes, it's leaking. I'm going back because I'm concerned about leaks, but not for cesium. Strontium-90, that number would only take 20 years to reach what happened in 2011, the current levels. And in fact, the other concern there is there's a lot of strontium-90 in the 1,000+ tanks that are on land where they're capturing some of the water before they can purify it. And if anything were to happen, we saw about a rain event a couple of weeks ago. We can talk about that in Q&A. But there's still a large source of radioactivity on land that I'm concerned about. Also fisheries, they've had to close fisheries, and I think we need longer studies about the source to those fish, whether it's the rivers, the seafloor, and other things, not just measuring fish. But the Japanese do a very good job of monitoring their food supply, much more so than any other country. And then decommissioning itself, it's going to take decades, billions of dollars, and these people who can't return home. Final couple things about looking to the future. I have with me a prototype made on a 3D printer of something we call the rad band. The thought is rather than collect 5 gallons of water, can we make it easier? And I think by wearing this device, you could collect basically the equivalent amount of cesium as we get out of something like 5 gallons of water. that could be mailed back to a lab for analyses, much easier than shipping 50 pounds of water across country. I think there's great potential for that, and in general, we're going to try and promote this through something I also think is kind of fun to tell audiences about. I was floored when this guy called me up, Ben LeCompte, and said, you know, I've got this plan. I can swim 8 hours a day. He's done this before. He actually swam across the Atlantic. And I want to go from Tokyo to San Francisco. It'll take about half a year. I'll be in the water 8 hours a day. They'll put me back in where I left off. And along the way, what I want to do is collect samples for you because we want to study oceans and use this as a platform to learn more about radioactivity. There's a group doing plastics. There's a group studying his own physiology changes as he goes along. And so what we'll be fundraising for in the next couple of months, both for the rad band itself, can we make this a marketable product, and basically for 100 samples, we're going to try and get 100 samples so we can actually cross the Pacific as he swims along on that. So it's very exciting stuff, and again, more information will show this website later in this upcoming swim across the Pacific. See what happens. I certainly think it will be quite a feat and interesting to see, you know, how well human power can take you that type of a distance. It'll be a challenge, but we'll see how it goes. Thank you very much. So Jay Cullen, you've been introduced, but here's Dr. Jay Cullen.
Thanks very much, Ken. Thanks to everybody for coming this evening, and thanks to the Aquarium for hosting this event. I'm going to talk about a Canadian contribution to this monitoring effort, and it's a project that was funded and came about largely due to public demand for quality, science-based information about what the likely impacts of the Fukushima disaster will be to the Canadian ocean ecosystem and to residents of Canada. And it was funded by MEOPAR, which is a mouthful, but it's part of the networks of centers of excellence that was set up by our federal government. It was set up in 2012 at Dalhousie University, and they're funding this project, this network of both academic and government scientists, as well as citizen science volunteers, to determine what the likely impact of this disaster will be on our waters and on our citizens. So INFORM stands for the Integrated Fukushima Ocean Radionuclide Monitoring Project. As I stated before, it's a collaboration between both government and academic scientists, international partners. Ken's research group is involved, and also citizen science volunteers who are collecting samples for us up and down the BC coast. It was funded by MEOPAR in August of 2014, and we'll be making measurements over the next 3 years until 2017, the period of time over which we expect this ocean-borne contamination from Fukushima to have the greatest impact that it's likely to have on our country. This is our network, our academic partners. We have scientists working at UVic, where I am, the University of Ottawa, the University of British Columbia, and Ken's research group at Woods Hole in the United States. Our government partners are working at Health Canada and the Department of Fisheries and Oceans. The INFORM project is really leveraging existing monitoring that had been going on, world-class work that was being done by our colleagues at Health Canada and DFO, but perhaps wasn't being communicated as quickly and as clearly as it could have been to the public. We're also working quite closely with non-governmental organizations that have been key to the success of this project thus far. We're working with the Georgia Strait Alliance, Living Oceans, Raincoast Education Society in Tofino, the David Suzuki Foundation, the Clayoquot Biosphere Trust, and the Surfrider Foundation. These organizations have helped us reach out to and coordinate our citizen science volunteers, and I'll talk a little bit more about how essential they have been, but I just want to highlight the fact that these organizations are doing fantastic work. And if you're at all interested in the health of the oceans and have a passion for that cause and making sure our oceans stay as pristine and as useful and as beautiful as we would like them to be, get in touch with these organizations. They're doing a great job. So what's the Inform project setting out to do? Well, primarily, we want to be making high-quality measurements of these potentially radiologically significant radioisotopes that were released from the Fukushima melted reactors. We're doing that by making measurements offshore, as Ken described. So on research vessels, we'll go out far offshore into the Northeast Pacific and Arctic Oceans to collect these samples to look for this contaminated water offshore. We're also working with our volunteers who are collecting samples for us along the coast, up and down the British Columbian coast. We're making measurements in marine biota. I'll talk in detail about the sorts of measurements we're making and why. And then the other important component of this project is education and outreach. We're working on getting this data in ways that are digestible and usable by the public online as quickly as we can. We're giving public lectures like this lecture to get the results out to people as quickly as we can. And we're developing online teaching tools. Dr. Erica Frank at UBC is working on online content that will help to educate people about ionizing radiation in the environment and what the health risks are associated with ionizing radiation in the environment. So, what are we looking at? Ken highlighted the utility of looking at cesium isotopes. These are artificial radionuclides that wouldn't be in the environment except for human activities. And what we focus on, and why we focus on them, is the isotopes 134, which has a relatively short half-life of 2 years, and 137, which has a longer half-life of about 30 years. We measure these isotopes because cesium-134 in particular serves as an unequivocal fingerprint of impact of the Fukushima disaster on a given sample, whether it's seawater or a living organism. That's because all the other human sources of this isotope to the environment have happened far enough in the past that that isotope has decayed away. So if we can detect cesium-134, we then know that that sample's been affected by the Fukushima disaster. Next to iodine-131 that Ken also mentioned, these isotopes were released in both significant enough quantities and are also biologically concentrated from the environment into organisms such that they're likely to, or the most likely isotopes to represent a radiological health risk to organisms and human beings here in Canada. And compared to other isotopes, they were released in relatively large amounts. So other isotopes that we might be concerned about, like plutonium isotopes or strontium-90, the amounts of cesium that were released, and also the propensity of those other isotopes like strontium and plutonium to concentrate in organisms is lower compared to cesium. And so we expect that if we can detect cesium in a sample, then we can have a very good handle on what the likely dose and therefore impact of the other isotopes are likely to be. If we can detect cesium, if we can't detect cesium, we're unlikely to detect these other isotopes. Part of our project is looking offshore, and this is work that's done in John Smith's laboratory. We're making measurements three times a year. Research cruises leave from Sydney, BC, and head out through the strait and out into the middle of the Northeast Pacific as part of the Line P time series that's operated by the Department of Fisheries and Oceans. We're collecting samples there. Ships of opportunity that go up to the Arctic, research icebreakers that leave from Victoria and cross the gyre. We're collecting samples each summer on those ships, and then we're also collecting samples in the Arctic to look for signs of Fukushima contamination. This is a schematic showing the locations of communities where we have citizen science volunteers who are collecting samples for us at the shoreline, literally right from the beach or from the dock. We had on the order of 600 volunteers who reached out to offer to help us. Starting in October of 2014, when we collected our first sample in Victoria, we have 14 sampling nodes where we're collecting a seawater sample every month to look for the timing of the arrival of this contamination and what levels we might expect. This part of the project is drawn directly from and borrowed directly from Ken's Our Radioactive Ocean program, which we've emulated here. We send out these kits free of charge to our volunteers in these communities from Victoria in the south to Lax Kw'alaams in the north, and they collect our sample for us and send it back to the lab for processing and analysis. And since about December 2014, we've had pretty much 100% network coverage. Without the enthusiasm and the passion that these volunteers have shown, our project wouldn't be a success. And I've had actually the pleasure of meeting some of these scientists. Here's some pictures showing Megan Ives. She and her family in Sandspit on Haida Gwaii collect samples for us. The Tsimshian Academy in Lac Squams goes out and collects water for us as well. We also have Cheryl Pavla in Prince Rupert, who collects samples for us. And for those of you who might be interested in helping out here in Vancouver, our coordinator here is Barb Carlin, and she, this coming Saturday, the 19th, will be at Vanier Park at noon to collect the sample. If you want to see how the sample is collected or help out or learn what we've been doing as part of the project, please do show up, participate. Again, it's people who care about the ocean who are helping us to understand what the impact of this disaster is here in Canada. We're also making measurements of the marine biota. This is a picture of a beautiful Pacific salmon, a wild salmon where we have our radionuclides that are dissolved in seawater, like salt. They can be taken up and concentrated by microorganisms and then up the food chain and be consumed by Pacific salmon. This is one of the ways that these contaminants can find their way into these organisms. They can also be circulated through the gills directly from the seawater, for example, into the fish. And working with Mark Trudell, who's a fisheries biologist with DFO, we're collecting on the order of 100 to 200 fish every year of the project and having those analyzed by scientists at Health Canada to look for signs of Fukushima contamination in these fish and what the levels might be, and therefore what the risk might be to other organisms that depend on these fish in the environment, and also because salmon are so culturally and economically important for us here in BC to understand what the potential dose to consumers of these fish, human consumers of these fish, might be. We've chose to focus on sockeye salmon and steelhead trout. The reason for that is that the migration patterns of these fish take them farther into the western Pacific than other species of salmon that return to BC rivers and streams every year. So we're collecting these fish. We're working with the Nisga'a Nation in the north who are helping us to collect these fish as well, but we're collecting fish from various runs up and down the coast of BC, fish that grow up in the Pacific and return to their home streams and rivers along our coast. This graph summarizes our results thus far. The key to understanding this figure is, of course, the fish location itself is showing the population or the river to which the salmon or steelhead trout were collected from as they returned. The bottom color of the fish shows whether or not there's cesium-134 that can be detected, again, that fingerprint of Fukushima impact. And the top shows cesium-137, the levels that we measure in the fish. And as you can see, all the fish that we collected, the roughly 100 fish that we collected in 2014, we were unable to detect any Fukushima-derived cesium-134 or 137 in these fish. What we see is a background level of contamination owing to the presence of 137 cesium in the North Pacific that goes back really to the Chernobyl disaster, but mostly from atmospheric weapons testing that happened in the last century. We can compare those numbers, roughly 0.25, a quarter of a becquerel per kilogram of cesium-137 in these fish, and compare it to the levels that are being measured by Japanese scientists in Japan, and fish that were collected off the coast of North America that had grown up in proximity to the reactors but migrated across the Pacific, these tuna populations, and our own results here that have been collected through Health Canada and the INFORM project. What we're seeing here, it's a rather busy figure, but you can see any red color indicates the presence of Fukushima-derived cesium, impact of Fukushima on the levels in these fish. And not surprisingly, fish that are collected close to the Fukushima melted reactors have higher levels of this artificial radionuclide in their flesh. The Japanese Fisheries Agency has analyzed on the order of 50,000 fish, both from Fukushima Prefecture and from adjoining prefectures, to monitor for what levels of contamination are being seen and whether or not those fish can go to market. Fisheries in Fukushima Prefecture remain closed at this point. But you can see also shown here are the regulatory levels the much more strict Japanese regulatory limit for cesium-137 in fish compared to the American, which is roughly equivalent to the Canadian regulatory limit. And we see that now, as we move forward in time from this very large release of isotopes that happened in 2011, even in Fukushima Prefecture, many of the fish that are collected offshore are now starting to meet that more stringent Japanese limit. We see that after the disaster, there was an increase in the artificial radiocesium in tuna that were collected off the coast of North America, levels far below these regulatory limits, though. And as of yet, the salmon that we've looked at, we don't see this impact of Fukushima on the levels of radiocesium in the fish at this point. Of course, in the harbor itself, at the destroyed reactors, we actually can collect fish, and the Japanese are still taking fish out of that harbor for monitoring purposes with quite elevated levels of radiocesium. The highest so far is a bottom-dwelling fish in contact with the sediments that had on the order of 750,000 becquerels per kilo. Obviously not something that one could consume in any safe way at all. So we do see these fish living in the harbor that are quite contaminated still, but as we move away from the source of this contamination, we see much lower levels in the fish that we're collecting here in our waters off of British Columbia. So just to summarize the results of our sampling through the INFORM project for the marine biota, we don't see any cesium-134 in the fish, no fingerprint of Fukushima impact on the salmon and steelhead trout that we've collected thus far. We do see cesium-137 in the fish at levels that were consistent with what was being measured before the Fukushima meltdowns occurred. Okay, so again, this is vestige 137 cesium left over from atmospheric weapons testing in the 20th century. It's a good baseline this first year for us to compare over the next number of years as this ocean-borne contamination has more of an impact on our coastal waters. We anticipate a peak in the seawater activities between 5 and 10 becquerels per meter cubed of cesium-137. Based on how it concentrates in fish, this should translate into an increase from this roughly 0.25, a quarter of a becquerel, to a half or 1 becquerel per kilo, given how we know this isotope tends to concentrate in fish. This compares to the Health Canada intervention level of 1,000 becquerels per kilo. So based on the contamination that we see offshore, sort of looking over the horizon, we're not predicting that levels should increase to the point where advisories or intervention and asking people not to eat these fish for their health will be necessary. You've probably all heard and been reading about some of the strange events that have been occurring along the North American coast, the Northeast Pacific, this temperature anomaly, the blob, the fact that we have an El Nino spinning up at present that looks like it's going to be a rather powerful one. There's been lots of marine mammal strandings, and the public wants to know whether or not these strandings and the death of these organisms is in any way related to the Fukushima disaster. And so being as proactive as we can be and obtaining samples when we can, we get samples of these mammals and we look for Fukushima-derived radioactivity in them. You might have, or you might remember, there was a young gray whale that was washed ashore on Wickaninnish Beach on Vancouver Island. We were able to obtain samples of the muscle and fat of this gray whale, and after very sensitive analysis, we were not able to detect artificial radiocesium in this organism, neither Fukushima-derived or this background that's present from weapons testing. So based on those analyses, it's very, very unlikely that the demise of this particular whale was in any way related to negative impacts of this ionizing radiation that we can detect with our sensitive instruments. But these levels simply won't lead to the sorts of health implications that would lead to the stranding and death of an organism like this gray whale. Similarly, to touch on other events, strange events in our waters, most of you are probably all aware of the sea star wasting syndrome that's shown up all along the coast of North America, basically from Baja up to Alaska. There's been some attempt or rationalization of this event in terms of the contamination from Fukushima causing this wasting. That's not what the scientific community understands about this wasting syndrome. In fact, to find scientists who work and conduct research here at the aquarium, we're involved in a very important publication where they demonstrated, this is a picture I took at Botanical Beach last summer, showing a sea star showing symptoms of wasting. They demonstrated that sea star wasting is actually related to a viral infection, and that the outbreak of the disease has actually happened before, but not on this sort of scale. We are starting to see populations of these sea stars recover. They're not near to the sorts of abundance that we saw before this mass mortality that started to show its head in 2013, and last year was particularly bad. But the levels of infection that are being seen along our coastlines tend to be lower than what we saw last year. So it does seem like these populations may be able to recover. But as a keystone species that helps shape the intertidal community, the loss of these organisms is a very interesting research question that we're going to continue to work on. But it's not related, as far as we understand, to ionizing radiation from the Fukushima disaster. So I'll wrap up here. To sum up, none of the fish that we've looked at thus far, these sockeye salmon and steelhead trout that returned in 2014, were found to have a Fukushima impact. No cesium-134 were detected in those organisms. We are starting to see low levels of Fukushima-derived radiocesium along our shoreline, as Ken pointed out in February in Ucluelet. The first sample with that, the presence of that isotope was collected at the beach there. What this means is that we don't see radioactivity from Fukushima yet in our fish. We've just collected 160 more fish this year. We'll continue to look for it. And we are starting to see the radioactivity, this contamination, showing up along our coast. But the levels are very low, even compared to our drinking water standard. We see nuclear weapons testing fallout radiocesium in both the fish and in the seawater. But when we look at the dose that one receives from that amount of radiocesium in fish that we might consume, it's very small compared to the dose that you receive from naturally occurring radioisotopes that are always in the fish. And the levels that we see of either these naturally occurring radioisotopes or the cesium-137, this artificial radionuclide, approach levels that are known to be dangerous either to the organisms or the marine ecosystem or human beings that would choose to consume those fish. I'll end by just thanking again the aquarium for hosting this event. I think it's a really useful opportunity to talk about what we've been doing and answer questions. So thanks again to the aquarium. And I'll point out that if you're interested in the project, I'm very easy to get a hold of. You can contact me by email. If you use social media, you can follow me and the project on Twitter. And this is our website for the project where we post our most recent results. And I also summarize the results of the most recent scientific peer-reviewed literature on Fukushima impacts in the environment. So papers that you might be frustrated that might be behind a paywall, I read all of those and I try and make notes and make it hopefully a little bit more straightforward and perhaps exciting to read. And that information can be found at the website as well. And I'll stop there. And at this point, I believe we can take questions.
All right, thank you very much, Jay and Ken. So what I'd like to go ahead and do is invite our speakers to come on up to the table that we have over here. I would also like to invite a manager for our Shoreline Cleanup Program, Caitlin Sweff. And I've invited our manager of Shoreline Cleanup here today because, we've been talking about radionuclides and radiation that's floating through the water, but there's a lot of other things floating in our water as well. And she works with thousands of Canadians every year to go out and look at the debris that we find on all of our coasts, wherever water meets land, basically, and track what's going on. So I thought I would go ahead and open up with a question for Kate, and I would like to ask a few questions, and then as I'm asking questions, if you have some, please feel free to raise your hand, and we'll come out and put the microphone in front of you. Kate, what are some of the most common items that we see washed up along shorelines here in Canada?
So a lot of people have been asking us what we find on the coast of BC from Japan and how we know it's from Japan. We find all kinds of things, and every time we find something that's from Japan, it's really a reminder of a human tragedy. I think we've sort of talked about here how it impacts us, but one of the things that tsunami debris reminds us is that 18,000 people died and 1,000 are still missing. And hundreds of thousands of people lost their homes and all their possessions. And we find some of these possessions on our shorelines here. Some of the things we can definitely trace back. So what I have sitting in front of me here is a fishing buoy from a fisherman in Japan. And this is a hand-painted symbol on here, which would just be used by one fisherman in Japan. Things like this, we know that they're from Japan. We can trace them to one individual. And there's lots of different things like this that we find on the shorelines. We also find lots of wood that comes from Japanese houses. It's very distinctive. So unfortunately, most of the things that we find on our shores are not returnable or not traceable to an individual. But when they are, it's a really nice way to show how connected we are to our neighbours across the Pacific Ocean. And it's also a reminder of a huge human tragedy and a massive loss of life.
Thank you very much. Caught me multitasking there. So there were a couple of points that Canon made in their presentations today about being able to swim or eat seafood in the ocean, but maybe we could just summarize that here briefly. Do we need to be concerned about swimming in the ocean, in the Pacific Ocean?
Well, the number I give often, I try and compare it to something where you're familiar with, dental x-rays, and it comes out to be a dose. The additional dose that you get from swimming, should cesium get up to the level of 10, we're not quite there yet, is about 1,000 times less than a single dental x-ray. Now, radioactivity, you have to watch out. It's never zero effect. There's always some additional chance, but there's a big difference, right, between one that's that small and what it was like off Japan when cesium levels were 50 million times higher. I would not be swimming in those waters. I would not tell you to swim in those waters. So we just have to think about the levels, and everyone can choose whether that's an acceptable risk or not. And again, I'll never tell you it's zero, but it's a very, very small number compared to other things we're exposed to.
Okay, very good. Safe to go in the water.
Yes.
Thank you. And maybe for Jay, do we need to be concerned about eating any of our seafood here in the Pacific?
Well, similar to the results I've just reported, all the measurements that we've made thus far on salmon indicate that the levels of artificial radionuclides haven't increased in those fish since the disaster. So the risks associated with consuming those fish are similarly unchanged. So to be very direct about it, again, to use Ken's approach of comparing it to behaviors that we choose that have risk associated with them, at the levels that we're seeing, the cesium-137 present in salmon, if one were to consume 20 kilos of salmon in a year, the dose that one experiences from consuming that fish is about 300-fold less significant than if you're a pack-a-day cigarette smoker. So one of the reasons smoking is bad for you is that the plants have naturally occurring radionuclides in, and when you inhale that smoke into your lungs, you introduce those isotopes directly into your lung tissue, and the dose that's associated with that is quite significant. So the short of it is you would need to eat 20 kilos of salmon at these levels every day to have the same dose that you experience from smoking cigarettes. So that gives, again, choices in behavior that lead to risk. It's not a zero risk, but it's a small risk.
All right, great, thanks. So sounds like not a major risk there. We're pretty safe to keep eating our salmon. We just don't have to eat 20 kilograms per day. How about the impacts to some of our beloved animals here in British Columbia, the orcas? Any concerns for them?
So it's not unheard of for an orca to consume 20 kilos of salmon in a day, especially our residents, that we're very concerned about the health of that population. There are modeling studies that have been done to try and understand what levels of cesium, for example, we might expect in those organisms. I think that as we make more measurements to characterize what the levels of radiocesium are in the habitat of these important mammals, and understand better what the levels are in their food, we're going to get a better understanding about what those maximum levels will be. As it stands, I don't think that the orca need any additional stress on them, but the levels that we might predict based on the seawater concentrations that we actually measure probably aren't a really significant health risk to those organisms.
Another question for Kate. Have you seen any interest from shoreline cleanup participants in the radiation that's coming along the BC coast in particular? Is there interest there in getting involved or concerns from folks that are already out there doing cleanups?
Yeah, people often ask us about radiation in the debris that we find. One of the key things about a lot of the debris is that it was actually from an area north of Fukushima, and that a lot of the stuff was washed out into the ocean before there were any problems with radiation at all. So a lot of the items hopefully didn't come into contact with a lot of the stuff coming out from the nuclear reactors. But people are really concerned about it over here, and they're asking us a lot of questions. But to the best of our knowledge, it's not something we need to be concerned about.
All right, great, thank you. So I'd like to go ahead and see if anybody in our audience here has any questions. Feel free to raise your hand, and we'll come on over and hold the microphone in front of you. Yep, and we'll hold it for you.
With
Yep.
Vancouver and Seattle being pretty big shipping areas, have you guys ever measured any of the water inside a shipping container or bilge?
So looking at radionuclides that are traveling over in bilge water. Yep, okay.
I'm not aware that anybody has made measurements on the bilge water for radionuclides. I know that there are individuals who are more concerned with invasive species, for example, in bilge water, and that's a major concern. But I'm not aware of any scientific studies that have reported measurements made in bilge water or anybody who's actively sampling it. But it's an interesting idea. There have been measurements of surface seawater made from ships of opportunity, shipping container ships who have collected samples for Japanese colleagues, for example. But the bilge water itself, I don't think so.
Just to add, when we go to Japan right now, we get about 1 kilometer from the reactors is what we're allowed to sample. We'll see numbers up to 1,000 of these becquerels per cubic meter today, what I expect in a few weeks. So if you were to get water from that site, it could be up to that many times higher. But short distances away, when we leave out of Tokyo or Yokohama to the North Sendai, we're down to levels that are more in the tens of those units. So you don't have to go very far from the reactors today to see much lower levels, even in the ocean off of Japan.
So a little bit higher than what we might see just in the water here. They could bring bilge water that has 10 becquerels or so, and then that could be discharged here. But again, that's a very low concentration, is
And
what you're
that's
saying.
the highest number,
Yeah.
and volume-wise, it'd be invasive species, I think, would be your
Yeah, okay,
biggest bilge concern.
great. We have another question right over here, Christine. Oh, she'll make her way across the theater and down a couple of rows. So, yeah, maybe meet her on the end of the aisle. That would be great. Thank you.
Have you guys found any traces of radiation on land animals like bears or birds that eat salmon and things like that come upstream?
I'm not aware of measurements that have found Fukushima-derived radionuclides in land animals. There's a nice study that's summarized on the Fukushima-informed site where scientists looked at mushrooms and soil samples that were collected up and down the western North American coast. Those mushrooms tend to concentrate these isotopes, and so there's a clear impact of Fukushima on the levels in the mushrooms, but still the bulk of radiocesium that are still measured in mushrooms today actually reflect atmospheric fallout from testing rather than Fukushima. But that's the only study I'm aware of where samples were collected on Vancouver Island looking at the impact on terrestrial organisms.
I might add, at least in Japan is where you might expect to see effects. And there's a scientist named Tim Mousseau who's studying birds, small mammals, insects, and looking for genetic anomalies. You may have read about some of the wing deformities, and they're seeing small effects as he gets closer to some of the hot spots in Japan on land. So this is where they're measurably higher and where there's still ongoing concern. All of these things, the way I think of it is always higher effects on land than in the ocean because things move around and get mixed in the ocean. And certainly the closer to the source, the higher the effects might be if you're looking for health effects or things on animals on land.
What's the reason for the difference between the regulatory limits in the U.S. and Japan?
I'll make a stab at one of them. They often pick those limits to say we won't see any measurable cancer above 1 in 20,000. They'll pick some number. About 1 in 3 people will develop cancer in their lifetime. So a government agency will be responsible to say, based upon our best knowledge, we want to keep the risk lower than 1 in 20,000. Now for fish, when I first went to Japan, their limit was twice as low as our limit, the Canadian and US limit, but they ate more than twice as much fish. So that made a lot of sense. They had 500, we had 1,000 becquerels per kilogram. They lowered it down to 100 just after, about a year later, and that was to kind of build confidence in the local population that, oh, things are going to be much better. We have the safest quality, we have the cleanest fish as far as radioactivity in the world. In fact, what it is built in a lot of confusion because there was no scientific basis for doing that. That was a political decision, and what it meant is you're telling some mom was feeding her kid that the food you fed them last year wasn't safe and now we're going to lower the standard. That's what the population basically heard. And so I think in some ways it was a public relations disaster. There might be good reason to keep them low, even lower, whatever you might consider your standard should be. But to change these things without giving any information, just all kinds of things happened. There were supermarkets in Japan that had different prices on products based upon how many becquerels of cesium was in a certain product called the becquerel wars. And so you'd go to the store and buy things based on cesium content. There's just all kinds of problems that came out of that. Very difficult question, though. What's the right number to pick?
Great, right here in the front. Oh, we have one in the back. Sorry, go ahead. We'll be down here in just a second.
I was just wondering, or my dad was wondering, if Fukushima was still releasing some water and radioactive elements into the ocean and when that's kind of estimated to end.
Yes, the short answer is there have been ongoing releases, so those red dots didn't go back down to 1 or 2. They're being maintained at higher levels. That's most likely due to groundwater input, not runoff over the surface. Things like the rain event from just a week or so ago. There was additional releases to the ocean as some of these holding tanks overflow. There have been human error. There have been leaks of tanks themselves that were not designed to be permanent for long-term storage. And they've leaked into the ocean. They're quite large amounts. So I guess the way I look at it depends upon the isotopes, but for cesium-137, 134, those leaks tend to be small relative to what happened 4.5 years ago. For other radionuclides, strontium-90, actually a somewhat larger health concern because it accumulates in bones. There's actually many more times strontium-90 held in those tanks, these 1,000 tanks, than were ever released. By our estimate, over 100 times more, it still remains on land in these holding tanks than was ever released. So should something happen, should things continue to happen, that's of concern. The groundwater is almost impossible to stop, and so that will continue for decades. But fortunately, those levels are low, but very hard to contain. Ice dams, things you can engineer to stop them, have never been done on this scale before, so it's hard to predict really what's going to happen in the future.
Right here in the front.
Yes, this is a very dynamic process in many different layers of dynamism that's going on here with species, cumulative effects of radiation upon various species, migrations of these species through different sectors of the oceans, and the dynamism or the dynamic of the unpredictables, the tanks, the holding tanks, which lots of people are quite concerned about, like what happened a week ago with this hurricane or water effect. leaking more highly radioactive water into the oceans. What you've presented this evening has been very reassuring for us who live in BC about the current state of the fish here. We've heard other people, including people from our community, that have been quite disturbed and have given up eating fish altogether. But what is the prognosis for the next 10 years? What can you as scientists actually tell about the level of strontium-90 and cesium-134, 137 as this moves through the food chains, as there is more coming to the West Coast in 2016? What kinds of things are you able to forecast?
So the question really gets at how well do we understand how these radionuclides behave in complex food webs and how they concentrate and potentially biomagnify in organisms. The short answer to that is that for these types of radionuclides, and if we want to focus in on cesium and strontium, these isotopes, the chemistry of these elements, mean that they behave or that they tend to be less biomagnified than elements like mercury that we know to be concerned of in fish that we consume, or organic contaminants like PCBs or PBDEs, contaminants that are problematic for orca, for example. The biological half-life outside of the physical decay of these radionuclides, for cesium, for example, we know that rather than just accumulating, if the seawater has a certain level, the fish don't continue to accumulate and accumulate and accumulate cesium because it's very chemically similar to elements like potassium. It turns over within the organism. So biomagnification of isotopes like that are less of a concern. Ultimately, it's the level in the seawater that will predict what will happen at the higher levels of the food chain. And based on what we see at this point, again, looking over the horizon and understanding as best we can what the leak rates are from the site now compared to what they were in 2011, these levels we don't think are going to be at levels that translate into problems up the food chain. But as Ken indicated before, the site itself and these extreme weather events highlight how precarious the situation is at the site. And if something dramatic happens and release rates approach what we saw in 2011, then we have to see what's in the seawater. We have to evaluate what might happen. But based on what we see now, I think the short answer is that we don't predict that these are going to accumulate to levels that will be problematic.
All right, we're going to take one online question, and maybe we can get over to our other next question here soon. So Kelsey Smith wants to know if there are any concerns for something similar to this happening here in BC or along the west coast of North America if there were to be an earthquake or some extreme weather event that caused a meltdown at a nuclear power plant.
The short answer is that British we don't have nuclear reactors that generate power, such that an event like what happened in Fukushima is unlikely to occur here. However, to our south, our American cousins do have reactors in California on the coast, quite close to active fault lines. And so it is possible that the same sort of scenario that occurred in Japan could happen with these older reactors that are placed on the California coast. I know that the NRC has been trying to use the Fukushima disaster as a way to improve safety standards at these plants, but I don't think anybody would say or could say that it couldn't happen along the west coast of North America.
Just like to point out as well that obviously the radiation is not the only impact of an earthquake and a tsunami, and that the tsunami in Japan is a really great reminder to all of us as well that we can be prepared here in BC and along the west coast of North America in general. We know that these events are coming, and people I've spoken to in Japan have really pointed out the importance of having a grab-and-go kit, having a plan with your family. And I think whenever we think about these kind of things and remember that so many people died in Japan, it's really worth reviewing that stuff with your family when you get a chance.
Yeah, that's a great point. Thank you very much, Kate. So we have another question. Let's take another question, and then we'll wrap up. And if anyone has further questions, we'll be down here after the presentation and Q&A, and you can ask questions directly with our presenters. So our last question here.
Thank you. I had a couple questions, but really what I want to ask is, can anyone, a scientist, physicist, or anyone, expert or not, really estimate the levels that are coming out of Fukushima on a daily basis? This rain event must have, I mean, the amount of water that probably went through that plant, how can anyone possibly estimate what's going on there? I think it's disingenuous to what's happening there to make these kind of assumptions, or, you know, that it probably won't be a problem in the future. How can anyone really say that? I mean, it's never happened before. People can, you know, it's still extremely dangerous place to work in, and if it's never happened before, how are people supposed to make these kind of estimates? Someone online at World Nuclear News told me a couple days ago that they estimate there's about 1 trillion becquerels coming out of there on an annual basis, and I don't know where these predictions can really be nailed down, and was wondering your opinion on that as a couple of good scientists.
These are fair points. I mean, it's never happened before. As we heard before the comments, it's somewhat unpredictable and dynamic. We didn't know we were going to have a foot of rain in an hour in parts of Japan. But what we can do quite precisely is measure what's, say, in the water in the ocean outside of that nuclear power plant. Probably the best way that I think, anyway, of monitoring what's coming from the plant is to be in the ocean near that plant and look at those concentrations as often as we can, as frequently as can, and independently from the government agencies or TEPCO, who actually are responsible for this site. And so that's what we tried to do. There's certainly not enough information. I was very frustrated after the rain event to find almost no information about the amount and levels that were in the ocean. In fact, there are some monitoring sites right in the harbor, and you can actually see the level of cesium go up from 1,000 in my units to about 3,000, so there was an impact. How long that's going to continue, I can't tell you because I haven't seen the whole record, but it's been frustrating to actually get enough information to make good predictions, and some of the spot sampling on land just doesn't tell you the net effect. But we do have, you know, stepping back, having said that, you know, we go back every year, twice a year, and you can measure quite precisely the concentrations in those waters that had to have come from that plant. And so people do make predictions then based upon the exchange of water, how much is coming out. And a colleague of mine, Matt Charette, looks at groundwater flow and measures actually chemicals that are coming, radioactive chemicals from that plant. So we have some estimates, and they all tend to agree that what's coming out today is much less severe than what was coming out 3.5 years ago when we had 50 million of these becquerels in the ocean, and today I see 1,000. It's not zero. But so we have some handle on it. How it's going to change in the future, we hope it gets back down to the levels that were near zero, but it never will be. It's going to be, for decades anyway, a site of continuous release, both through exchange, through those reactor buildings, and hopefully very few additional leaks. But that's what keeps me up at night, are continuous leaks that could happen at that site.
All right. I'd like to go ahead and thank our presenters and our guests here tonight, Dr. Jay Cullen, Dr. Ken Bissler, Kate LeSoif. Thank you very much for coming and sharing your expertise with us this evening. I'd like to thank all of you for coming out tonight and informing yourselves of what's going on and getting a nice scientific perspective on it. If you have any questions, you can contact us or put them in the our YouTube online comment section. Our next program will be on October 7th. It's in the evening at 6:30 p.m. and it's a little bit different. We're going to walk on the wild side a bit and go with Ocean Networks Canada and visit the seafloor right off of the British Columbia coast and look at some hydrothermal vents. So we hope that you can join us for that. Thank you very much and have a good night.